Galaxy clusters form the largest structures in the universe. The background image here is one of the closest and most studied galaxy clusters, Perseus, and it contains over 1,000 galaxies.
In this talk, we will discuss dynamical friction and two important examples, supermassive black hole binaries and the mass distribution of galaxy clusters. Then we will talk about determining the masses of galaxy clusters with three different methods.
Let's imagine a massive object traveling through a field of uniformly distributed, less massive objects. The body will gravitationally interact with the others, giving them an energy and momentum boost as it passes by. From conservation laws, the massive body will lose some of its own energy and momentum, leaving a wake of stars in its path. This effect is called dynamical friction, or gravitational drag. However, it is perhaps poorly titled because the friction that we know from Physics 1 is not a conservative force. Dynamical friction is what enables NASA to perform gravity assists to slingshot spacecraft and satellites further out into space. The craft essentially steals some of a planet's rotational energy, giving it the boost it needs to go further out. But the motions of the yellow objects here are exaggerated for the sake of the visual. Let's look more closely at just one interaction, where a massive object moves at a constant initial velocity past a stationary, less massive object. We will call the distance at closest approach b-min, sometimes referred to as the impact parameter. A part of the object's energy is transferred to the smaller body. The trajectory changes a negligible amount since in a close encounter, the radius of the object is much less than the distance of closest approach. It then continues at a slightly slower velocity, v, and travels a distance, vt. Now the shortest distance between the two objects is r. By integrating the gravitational force, we arrive at the change in perpendicular velocity. Through conservation of momentum and energy, we can find the deacceleration of the object. Capital lambda here is the ratio of b-min and the characteristic size of the whole system, b-max. Therefore, more massive objects experience more drag. And here is the condition of close approach when the trajectory barely changes. It is a strong encounter when the masses are comparable. For the force, we have this approximation. The surroundings are not always stellar. That term, stellar background, for the density profile is used when applied to dynamics of objects in a galaxy. In the case of the gravitational assist I mentioned, the surroundings are the planets and the sun. It can also refer to galaxies in a galaxy cluster, which we will come to. Dynamical friction is highly dependent on whatever that background may be, not only from the density term, but also from the function c, which represents the relationship between the velocity of the object and the velocity dispersion of the system. For example, c is 23 for the Large Magellanic Cloud and 76 for globular clusters. So now let's talk about two examples where dynamical friction plays an important role. Firstly, the merger of galaxies, an important process in galactic evolution. Let's take two galaxies, each with its own supermassive black hole at the center, now as a merger remnant. After the merger, the two black holes are then, for for our purposes, than a uniform field of stars. Just one interaction is not enough to decay the orbit of the black holes, but after many close encounters and over a long period of time, dynamical friction will slow their velocities and the black holes will gradually spiral in towards the center of mass. This is the first step in forming a supermassive black hole binary. The graph on the right shows a model of the decrease in the binary separation, A, on the y-axis as a function of the simulation time. Different colors represent different density profiles of the stellar background.
Just as causing those supermassive black holes to congregate at the center of mass, so do massive galaxies in a galaxy cluster. Assuming we have a spherical cluster, dynamical friction leads to brighter, more massive galaxies at the center of the cluster, which is easily seen here in this example of Abel 1689.
So now let's talk about determining the masses of galaxy clusters, which is commonly done in 3 ways listed here: hydrostatic equilibrium, the velocity dispersions of the galaxies within the cluster, and gravitational lensing.
First up is hydrostatic equilibrium. It is reasonable for us to assume that clusters are in a hydrostatic equilibrium, where the outward pressure is balanced by the inward pull of gravity. This first equation is familiar to us from Fundamentals 1. It is also referred to as the pressure gradient. Rearranging this equation and using the ideal gas law of a fully ionized gas, we can arrive at an equation for the mass. The other unknown properties, temperature and density, we can find through observations.
Next, we have the galaxy velocity dispersions. I've already stated that velocity dispersion plays a part in the dynamical friction force an object experiences. Its relation to the mass can be derived by starting with the virial theorem, where sigma is the velocity, and the beta parameter depends on the density profile used. Finding the density and temperature of the hot gas in the cluster will tell about the gravitational potential energy. The velocities of the individual galaxies within the cluster can also be measured from spectra to help determine the velocity dispersion.
The third and final method of determining the mass of a galaxy cluster we will discuss is gravitational lensing. Dark matter surrounding the cluster acts as a lens by bending the light. Objects behind the cluster are warped around the edges and the cluster itself is magnified, so the amount of lensing is determined by the mass of the cluster. The geometry is fairly simple. Here the source is at point L and the observer is at point O. After some simple trigonometry, we can solve for the mass, where the angle beta is broken into 2 smaller angles, theta 1 and theta 2. From this, we can also find a special parameter called the Einstein radius, which describes the angular radius of a ring that appears around the source when you have perfect alignment.
Let's go back to that image of Abel 1689, where the lensing effects can clearly be seen. Background galaxies around the edges are warped into arcs. This figure shows the mass enclosed on the y-axis in terms of solar mass. The scaled radius is on the x-axis. Each of the lines here represent different dark matter density profiles, with the dashed line being the familiar NFW profile. theta in represents the inner radius of the cluster. The theta e's at the top are that angular Einstein radii, which mark where the effects of lensing are weak and strong, respectively. This graph is not of Abel 1689. It is simply an example of a model. So, to summarize, we learned about dynamical friction and discussed a few different important cases, such as energy boosts for satellites and spacecraft, the formation of supermassive black hole binaries after the merger of two galaxies, and the structure of galaxy clusters. Then there are three common methods for determining the total mass of a galaxy cluster. Hydrostatic equilibrium, which is the balancing of pressure and gravity, measuring the velocity of galaxies within the cluster, and finally gravitational lensing, which is when dark matter acts like a lens, which is dependent on the mass of the source. And with that, I'd be happy to take any questions.